Today we are going to discuss important points from the theory of complex numbers and a connected topic, quadratic equations. Okay. Well, we are actually introduced to these topics in the reverse way. We first study quadratic equations, the quadratic formula, and then we introduce ourselves to complex numbers, and then we see actually the connection. The connection between complex numbers and quadratic equations is very clear. Okay. Uh, if you see the hierarchy of numbers, we in school we first define the set of natural numbers, then we define the set of whole numbers, then we define the set of integers, then we define the set of rational numbers, then we define the set of real numbers, and ultimately we define the set of complex numbers. Okay, then we define the set of complex numbers. Now, if you realize why is there such a hierarchy among numbers, okay, that hierarchy is there because each set except the last one, okay, each set except the last one is unable to solve some polynomial equations. Like for example, if I take the set of natural numbers, I cannot solve x plus 2 equal to 2 then. I can solve it in the set of whole numbers, but then I cannot solve equations of the kind x plus 3 equal to 2 then. Okay, so hence we go to set of integers. Okay, but even in the case of integer, if I say 2x plus 3 equal to 0, I cannot solve it in the set of integers. I need the set of rational numbers. Okay, I need the set of rational numbers there. Okay, but if I take the quadratic equation x squared minus 5 equal to 0, I cannot solve it in the set of rational numbers, so I have to define the set of real numbers. And similarly, if I ask what is x squared plus 5 equal to 0's root or roots, then I cannot solve that particular equation in the set of real numbers, and that is the need of defining complex numbers. Okay, that is the need of defining complex numbers. And there is a fundamental theorem of algebra here, like we have fundamental theorem of integral calculus, which says that if we have a polynomial equation whose coefficients are complex numbers of nth degree, then it is going to have n roots in the set of complex numbers. Meaning, it is never going to happen that you have a polynomial equation of nth degree having complex coefficients not having a root in the set of complex numbers. See, whether we are able to find those roots or not, that is not an issue. The issue is about existence. They do exist. Okay, so we can say that the set of complex numbers is the complete set, the most complete set, which contains the roots of all existing polynomial equations. Okay. Alright, so let us quickly discuss the need of defining complex numbers. So here is a quadratic equation, standard form ax squared plus bx plus c equal to 0, and we say that a, b, and c are real numbers. Okay, a, b and c are real numbers. We use the very well known quadratic formula which we obtain by completing the square, that is negative b plus or minus root of b squared minus 4ac upon 2. Okay, now when b squared minus 4ac, we call it discriminant, correct? B squared minus 4ac, this expression is called discriminant. Discriminant delta. Now when delta is greater than or equal to 0, the set of real numbers contains the solutions. But when delta is less than 0, then the set of real numbers does not contain roots of that particular quadratic equation, and an example of that is x squared plus 5 equal to 0. How much is the discriminant in x squared plus 5? Anyone? What is the discriminant of x squared plus 5 equal to 0? Negative root 5. Oh sorry, root minus 5. B, oh wait, not minus 5, minus 20. Right? B is 0, A is 1, C is 5, so 0 squared, 0 minus 4 into A into C. A is 1 and C is 5, so 5 into 4, 20. That's negative. So we cannot solve it in the set of real numbers. And that is the need. What is the need? The need is some quadratic equations. Well, I should not say some infinitely many, but just to put my point, I am making that statement. Some quadratic equations with real coefficients. Some quadratic equations with real coefficients do not have real roots. Hence we define complex numbers. Okay, hence we define complex numbers. Okay, so the need should be clear to us. Why are we studying this topic? What is its use? Fine. Acha. So let us now start with the definitions. The first definition is root of -1. Okay, the first definition is root of -1. We use the Greek alphabet called iota, okay, to denote that root. It's root of -1. But while pronouncing, I will just say I, okay, but it's actually a Greek letter iota, just like alpha, beta, gamma, delta, okay. So by definition, I squared becomes -1, okay, I squared becomes -1, I cube becomes -I, and I raised to 4 becomes 1, I raised to 4 becomes 1. So in general, okay, in general we can conclude by observing this pattern. Okay, and we can also have 1 upon I then. Okay, let's also continue with this. What is 1 upon I? I raised to 4 upon I, so that will be I cubed. 1 upon I squared is -1. 1 upon I cubed is I, and 1 upon I raised to 4 is I. Okay, so in conclusion, we can immediately see these results. That I raised to 4k is always 1. I raised to 4k plus 1 is always I raised to 4k plus 2 is always -I, and I raised to 4k plus 3 is always what? Negative. Okay, wait, I think I made a mistake. This should be -1, this should be -1, and I raised to 4k plus 3 is -I, where k belongs to the set of integers, both positive and negative. Have you followed this? The fundamental, or I would say the main definition of the whole complex numbers topic is this. Everything stems out of this. Okay, iota I equal to root of -. Okay. Alright, now let us go to the definition of complex number. Standard letter that we use to denote any complex number is Z. Please understand that this Z has nothing to do with the capital Z that we use to denote the set of integers. They are not connected to each other. Okay? Fine. So what is Z? Z is x plus iy. Okay, x plus iy. But what are x and y? X and y are real numbers. X and y are real numbers, and I is root of -1. Okay. You may know this, well, you will know this, you do know this, but I'll just add one point here. When we use letters to denote a complex number, or both real and imaginary parts, we always write I first and then its imaginary part. But we always write the number first and then the imaginary part if it is a number. Okay, so 2 plus 3i is preferred over 2 plus i3. Okay, 2 plus 3i is preferred over 2 plus i3, but x plus iy is preferred over x plus yi. Okay, real part of Z, it is always x, and what is the imaginary part? It is not iy, it is y. Okay, it is y. What do we call those numbers whose real part is 0? Purely imaginary numbers, correct? Purely imaginary numbers. And what do we call those numbers whose imaginary part is 0? Of course they are real. Okay, definition clear, powers of I clear. Part 3. We now define a term called complex conjugate. Okay, we now define a term called complex conjugate, and this number or this term plays a very important role in division of complex numbers. How do we define it? We denote it by z bar. If z is x plus iy, z bar is x minus iy. Okay, if z is x plus iy, then z bar is x minus iy. So I have to change the sign of the imaginary part to get its complex conjugate. Okay, so some properties immediately follow. Z bar is z. Okay, etc. We'll see those properties later. But is that clear? Complex conjugate definition. Okay, now we go to algebra of complex numbers. The 0th point is important. Okay, there is no comparison among complex numbers. There is no comparison among complex numbers. Okay, which means either z1 will be equal to z2 or z1 will not be equal to z2. We cannot say z1 is greater than z2 or z1 is smaller than z2. That is only there in real numbers. Okay, so either z1 will be equal to z2 or z1 will not be equal to z2. Okay, when will z1 and z2 be equal? If and only if, that's a biconditional statement. If and only if real part of z1 equals real part of z2, comma, imaginary part of z1 equals imaginary part of z2. Okay, there is no comparison among complex numbers. Next, how do we define addition of two complex numbers? Addition of the real parts plus addition of the imaginary parts. How do we define the subtraction? Subtraction of the imaginary parts and subtraction of the real parts and subtraction of the imaginary. The procedure that we follow in defining the product is a bit different. And this is where we make use of the fact that iota squared or I squared is 1. Negative, I'm sorry, negative. Okay, I'm just doing it as a revision. You people already know it, but let's do it. x1, x2. Okay, plus iota times x1, y2 plus iota times x2, y1, and then we have I squared here, I squared y1, y2, so that will be negative y1, y2. Okay, that is as far as the product is concerned. And what about division? The division is, well, we basically do two products here. That is, we multiply the numerator by the complex conjugate of the denominator, and we also multiply the denominator by the complex conjugate of the denominator. Okay, so it is z1 into z2 bar, and it is interesting to note the product in the denominator. We can use a plus b, a minus b, which is a squared minus b squared. But b squared is actually negative y squared, so here it will be x2 squared plus y2 squared. Is that clear? x2 squared plus y2 squared. Now, just an off-topic point. You people may remember that we have problems of the following kind in partial fractions. Okay, say x squared plus 5x plus 6. Okay, 5x, let's say minus 6, or x squared, wait. Squared, let's say 9. Now you know its integration. Okay, you know its integration. Okay, wait, let me just frame a question a bit. I just want to emphasize here a bit. Okay, suppose I want to build a quadratic equation whose roots are 2 plus 3i, 2 minus 3i, then what will it be? X squared minus 4x plus 13 equal to, yeah, okay. So, let's consider the integral of this. So, let us consider the integral of this. So, let us consider the integral of x squared minus 4x plus 13 equal to, yeah, okay. So, let's consider the integral of x squared minus 4x plus 13 equal to, yeah, okay. So, let's consider the integral of x squared minus 4x plus 13 equal to, yeah, okay. So, let's consider the integral of this. Okay, let's consider the integral of this. Now in NCERT they say this is a quadratic factor which cannot be factorized further. Okay, which cannot be factorized further, but actually it can be factorized. It can be factorized into x minus 2 plus 3i in a bracket and x plus 2 plus 3i in a bracket. So you can do it. Okay, you can factorize it, but the problem is we do not bring in any complex number while using the integrals of real valued functions. Okay, so we cannot use them because these numbers simply do not belong to the domains of our functions, but it can be done and you will also get results. So, well, the thing that brought me to that is when you multiply a complex number by its complex conjugate, you are always going to get a positive number given that the given complex number is not 0. Okay, is that clear? So when we will discuss integration by partial fractions in detail, I'll remind you that you can also solve the same problem by this method. Okay, you can also solve that problem by this particular method. Okay, so product is clear, division is clear. Usually we do not discuss product at this level, powers at this level, because we know that z raised to n can be easily found out if we know the exponential form. But you now realize that if I indeed want to expand x plus I y raised to n, I need to use binomial theorem if n is a natural number or even a real number. That's fine. Okay, we have to use binomial theorem. We will not be discussing x plus I y raised to some complex power. So assuming that n is a real number, we can happily use the binomial theorem. Okay, we can use binomial theorem ax and b will be iy. Okay, fine. So that is the algebra. Now let us discuss some useful properties of z bar, that is complex conjugates. Okay, now we are not going to prove these properties because we do not have that much time. You can do that. Is it okay if we verify these properties for two chosen complex numbers? Will that is that okay? Okay, fine. So let's do it. Let me take z1 as 2 plus 3i and let me take z2 as, let's say, 4 minus 5. Okay, let's do it. What is z1 plus z2? 6 minus 2i. What is z1 minus z2? Negative 2 minus 8i. Can you tell me the product quickly? z1 into z2. Okay, let's do it. 2 into 4, 8. 3 into 5, 15. Negative 15 I squared, so that will be positive 15. Imaginary part 12 minus 10. 10 parts, so 23 plus 2i. Okay, now let's do z1 upon z2 here. 2 plus 3i upon 4 minus 5i. Okay, that is negative 7 upon 1, 7 upon 41 plus 22 upon 41. That is z1 upon z2. Now let's verify all these results. Okay. Yes. Product is wrong. Oh, plus it. Yeah. Plus it. Okay. Plus. Okay. Now let us add z1 bar and z2 bar. Okay. Let us add z1 bar and z2 bar. 2 minus 3i plus 4 plus 5i. That's 6 plus 2i, that is the complex conjugate of this. Okay, so we have verified the first property. Okay, we have verified the first property. Property number 2, let us subtract the complex conjugate of the second from that of the first. Okay, So what is the complex conjugate of second? That's 4 plus 5i, but I need to put a bracket here. Okay, and I'll subtract this first. 2 minus 3i, negative to minus 8i, so second property is verified. Okay, second property is verified. Third, the product. It says z1 z2 bar is z1 bar into z2 bar. Is it true? Indeed, has to be. Let's see. Okay, let me put a bracket here. Let me put another bracket here. And let us now multiply these two complex numbers. The answer expected 23 minus 2i. The answer expected is right. 23 minus 2i. Now let's verify the last property. Z1 upon Z2 bar is Z1 bar upon Z2 bar. Okay. Fine. So I can just divide here. What answer are we expecting? Negative 7 upon 41 minus 22 upon 41. Yeah, that's right. Okay. So remember these results for bar, because see, for modulus of complex number, we can always use the polar form r e to the power I theta, which immediately leads to results like product of the moduli is moduli of the modulus of the products. Okay, so we'll see those results later, but these are main, or I would say basic results. Okay, no doubt in these? No doubt? Okay. Now let's see one more result. Suppose we have a polynomial. Okay, suppose we have a polynomial in z of nth degree. We are calling it p of z. Okay, we are calling it p of z. So that's a polynomial. So it is summation aj zj raised to z raised to j, as j goes from 0 to n. Okay, that goes from 0 to n. If this is the polynomial, and let's say we want to determine the complex conjugate of the value of the polynomial at the given number z, that means we want to determine pz bar. So pz will be obtained first, and then we will be taking its complex conjugate. That is as good as saying, let's take the complex conjugate of every coefficient a0, a1, a2, a3 up to an, and let us multiply this by what? The powers of the complex conjugate of z. Okay, this is a very useful result to know. Okay, and then summation first as j goes from 0 to n. Okay, let's verify this result for the given quadratic function. IZ squared minus 6z plus 3 plus 4i, and z is equal to 4 plus 5i. Okay, fine. So let's first find out the left side. P of z is equal to IZ squared. So I into 4 plus 5i bracket square minus 6 into z. Okay, plus the constant term is 3 plus 4. And now let us find out P of z bar. By the theorem, or by this result, it says take the complex conjugate of all the coefficients. Complex conjugate of I, negative 1. Complex conjugate of 6, 6. Complex conjugate of 3 plus 4i, 3 minus 4i. Okay, inside here. We also require to take the complex conjugate of z's. Okay, so 4 minus 5i, but don't forget that here we have got square. Okay, now let's see if that result matches. Okay. Acha. First I into bracket 4 plus 5i bracket closed squared minus 6 into bracket 4 plus 5i bracket closed plus, well, no need to put bracket here, but I want to emphasize that it's a constant term, so I'm putting a bracket, negative 61 minus 35i. Negative 61 minus 35i. Okay? Fine. Now, if we take the complex conjugate of this, it will be negative 61 plus 35i. That is the answer that we are expecting from pz the whole bar. Okay? Let's see. Let's see. What change will we make in 3 plus 4i? 3 minus 4 plus 5i, 4 minus 5. Minus 6, no change. 4 plus 5i squared, 4 minus 5i squared. Okay, wait. I, negative I, and 4 minus 6. Okay. So everything has been complex conjugated, right? See what result we got. Negative 61 plus 35i. Okay, so this property could be useful, that if we want to find out the value of the polynomial function at a complex conjugate of a given number, it is actually the complex conjugate of the value of the original polynomial. Understood? Yes. I hope you understood this. If you don't, please tell me, I'll explain. Everybody understood this? Okay. See, I also want to draw your attention to the following. Okay, look. See, suppose if I ask you P of Z bar, that will be A naught plus A1 Z bar plus A2 Z bar squared up to AN Z bar raised to 1. Okay, and if I ask you what is P bar of Z, then it will be A naught bar plus A1 bar Z plus A2 bar Z squared, so on till AN bar Z raised to 1. But please note that these are 4 different things. Which 4? P of Z bar is different, P of Z bar is different, P bar of Z is different, P of Z is different, and PZ whole bar is different. Everything is different. Okay? So we now have, we can say we have 4 polynomials. Okay, which are represented by similar symbols. What are they? P of Z, the main polynomial, Pz bar second, P of Z bar third, P bar of Z fourth. Quite often, if such situations arise in the problem, we tend to confuse ourselves a lot. Okay, but now we have made it clear. The bar signifies, or its position precisely signifies what is meant. Okay, what is meant. This is P of Z first, Pz the whole bar second, Pz bar third, and P bar Z is fourth. Do you follow this? Yes? Okay. Next, if we have a rational function R of Z equal to P of Z upon Q of Z, where P and Q are polynomials in Z and Q of Z is not equal to 0, then RZ bar is equal to PZ bar upon QZ bar. That means the complex conjugate of the whole. Okay, and we know this. So let's verify it for this. The P of Z is I plus 4Z minus 2 plus 3I Z squared. Q of Z is I Z cube minus 4Z squared plus 6I, and Z is equal to 3 plus 2I. Can you help me in let me write it. Fine. Can you help me in writing P of Z? I plus 4 into Z 3 plus 2I minus 2 plus 3I into 3 plus 2I squared. Q of Z will be I oh sorry, no, q of z is what? I z cube. I into 3 plus 2i cubed minus 4 into 3 plus 2i squared plus 6i. Okay, let's find this. I hope this calculator can, okay, it divides so it can handle this. Okay, iota plus 4 into 3 plus 2 iota I minus bracket 2 plus 3 I bracket closed into 3 plus 2i bracket closed squared. That's the numerator. Now let's go to the denominator. I into bracket 3 plus 2i bracket closed cubed minus 4 into bracket 3 plus 2i bracket closed squared plus 6i. Okay, that's negative 326 upon whatever that is. Okay, see, we are doing this just to get the feel of how the result works. Okay, the result is easier to remember. Acha. Now, can someone tell me what will be p bar of z upon, well, pz the whole bar upon qz the whole bar? No, we know the result. We know the result. I want you to tell me the numerator and the denominator. Yes. Let's start with the numerator. Complex conjugate of I, negative I. Complex conjugate of 4, 4. Complex conjugate of 3 plus 2i, 3 minus 2i. Minus. Here it should be 2 minus 3i. Here it should be 3 minus 2i squared. In the denominator it will be negative I into 3 minus 2i cubed. Complex conjugate of negative 4 is negative 4. 3 minus 2i squared minus 6i. Okay, so answer to this is the same with the negative sign in between. Okay, let's verify. Now to avoid confusion, I'm going to retype that. Negative I plus 4 into bracket 3 minus 2i, okay, bracket closed, minus bracket 2 minus 3i bracket closed into bracket 3 minus 2i bracket closed square. Denominator negative I into bracket 3 minus 2i bracket closed cubed minus 4 into bracket 3 minus 2i bracket closed squared minus 6i. See? So we have verified this result also. Could be useful in solving some problems. Okay? This deals with rational functions. Do you follow this? Okay. Well, if q of z is 1, then this result is basically the previous result. Okay, fine. Okay, one more result. We'll just read it. If z is equal to the determinant a1, a2, a3, b1, b2, b3, c1, c2, c3, where all of these belong to the set of complex numbers, then the determinant of the complex conjugate, complex conjugate of the determinant is equal to the determinant of the complex conjugates. Now the reason why I included this right here is we usually have determinants with the thing applicable to one row each. For example, if we define a determinant, let's say capital T, by f1 g1 h1, f2 g2 h2, f3 g3 h3, and where they are functions of x, and what is the derivative of this determinant? it's not the derivative, it's not the determinant of the derivative, if you remember. It is f1 prime, g1 prime, h1 prime, then f2, g2, h2 as it is, f3, g3, h3 as it is, and then what happens? Then we differentiate the functions in the second row. Then we differentiate the functions in the second row, and at last we differentiate the functions in the third. Okay, do you know this result or remember this result? F3 prime, very good. G3 prime and H3 prime. No, they will set the functions that way, don't worry. But my main point of including this property is this is a bit unusual about determinants, especially when the integers are complex numbers. Z bar is the determinant of complex conjugates. Is that clear? Let me add a note here. Okay. This property is unique. Because unlike differentiation, we do not conjugate row-wise. And add. Rather, we conjugate the whole determinant. Okay, we conjugate the whole determinant. Is that clear? Well, the result is easy. The moment you see the result, you get to know what it is telling. But because it is something different than what we know about derivative of a determinant, I included. Okay, let's now discuss a few more terms. First one is modulus. Okay, modulus of a complex number. Okay, modulus of a complex number, z denoted by mod z, also denoted by r, defined as positive or non-negative square root of the square of the real part and square of the imaginary part. Okay, that is modulus of z. To define modulus of z, you don't need Argand diagram. Okay, but to define the argument of z, we do need the Argand diagram. Okay, or otherwise we have to classify and consider different combinations of x and y, especially their signs. Okay, fine. So modulus of z is clear. Now to define the argument, we take the help of Argand diagram. So what is Argand diagram? Argand diagram is basically a plane which forms, rather whose points form a one-to-one correspondence. Okay, a one-to-one correspondence with complex numbers. Okay, let me put it in this way, with elements of C. Essentially, point P x comma y, whose coordinates are x comma y, represents the complex number x plus I. When that is there, we call it Argand diagram. There is nothing unusual about Argand diagram. Okay, some people have this, I would say, notion that if the imaginary part of complex number is imaginary, how can we show it? Okay, how can we show it? But see, in mathematics, the term imaginary does not mean anything that we say imaginary. Otherwise, even the number 2 itself is imaginary, because numbers themselves are an abstract construct. We can say I have one laptop, you have 2 mobiles, somebody else has 3 cars, or temperature is so and so decimals, we can say that. Okay, but numbers themselves are, when viewed from mathematical perspective, they are basically abstract objects, mathematical objects. Okay, they don't have a physical existence. Correct? So don't get confused. Both real and imaginary numbers, so to speak, are abstract. Okay, just to keep in mind, they follow certain rules, and using those rules we can build new elements belonging to the same set. Okay, yes. So coming back to the Argand diagram discussions, point represents a complex number and there is one-to-one correspondence. Okay, there is one-to-one correspondence. What is meant by that, one-to-one correspondence? It means no point on the Argand diagram can represent multiple numbers. 1 point, one number. And number two, no element from the set of complex numbers can be linked to two different points. Okay, that is what we call one-to-one correspondence. Okay, is that clear? Fine. No doubt, right? No doubt? Okay, very good. Now, on x-axis, we represent the real part of set. Okay, and on y-axis, we represent the imaginary part of set. Well, that obviously follows, but real part is horizontal, imaginary part is vertical, and this helps in the definition of argument. Okay, we can again define mod z or r as the distance between the origin and the point P. Okay, distance between origin and the point P, and that defines the complex number. That can also be obtained by using the distance formula. Okay, root of x squared plus y squared. But the definition of argument is, well, slightly different. Okay, because argument is a multi-valued quantity. Okay, so what is the argument of that? Angle between OP and positive x-axis measured, okay, measured from x-axis. Okay, so it is basically a directed angle, anti-clockwise positive, clockwise negative. Okay, now agreed that argument is multi-valued, when this argument lies between negative pi and positive pi included, negative pi excluded, we call it principal argument. What do we call it? Principal argument. Okay, what is principal argument? Principal argument refers to, well, we usually denote it by capital A. Okay, argument Z such that argument always lies between pi and negative pi, or you can say open interval negative pi, closed interval pi. Okay, that is called principal argument. Do you follow this? Argument part is it clear? The argument part? Yes. Okay. Now I will write down some complex numbers here. Let's try to determine the range of the principal argument. Okay. Meaning, is it between 0 to 90 degrees, 90 to 180, or 0 to negative 90, or negative 90 to negative 180. Okay. Let's do that exercise, because quite often we tend to remember it as tan inverse of y upon x, but that is not always the case. Right? That is not always the case. Okay, let's do this exercise. Okay, 2 plus 3i. Come on, 2 plus 3i is principal argument. Acute, obtuse, negative, acute, negative, obtuse. Yes, positive, acute, because it lies in the first quadrant. 2 minus 3i. On Argand diagram, where does this number lie? First quadrant, second, third, or fourth? Fourth quadrant. So negative acute. Got it? Okay. Negative 2 plus 3i. Second quadrant. So positive obtuse. Right? Positive obtuse. And negative 2 minus 3i. Negative obtuse. Negative obtuse. Correct. 2. It is 0. It is 0. Degrees or radians doesn't matter. 3i. What will be the principal argument of 3i? Anyone? Pi by 2. Right? Pi by 2 because it lies on the positive y-axis. Negative 2. Pi, not negative pi. Okay? Because pi is included, negative pi used to be excluded. Correct. Negative 3i. Yes, don't say 3 pi by 2. Although 3 pi by 2 is right, we are only considering the principal argument. So negative pi by 2. Okay. Well, now 4 more. 1i minus 1 minus I. These numbers are particularly important. 1i, negative 1, negative I. 1, 0, I, pi by 2, negative 1, pi, and negative I, negative pi by 2. Have you understood what is principal argument?
Yes, sir.
Yes. Now, see, there is no harm in remembering this formula. But please note that this formula is not always right. Okay? Modifications are required if x and y or x or and y are not positive. Okay? So you know what that means. Okay? You know what that means. Okay? Fine. That's principal argument. Okay. Now we go to polar form and exponential form. I find the exponential form the most suitable form for calculations. Okay? What is polar form? Anyone? Suppose we have a complex. Yes. Suppose mod z is r and principal argument, not exactly, but let's call it principal argument, let's say theta. And z is x plus r, of course. Z is x plus I. Okay. So what will be the polar form? In the polar form, we literally use the polar coordinates. So z is equal to r cos theta plus I r sin theta. R bracket cos theta plus I sin theta. Okay, so that's polar form. What is exponential form? Anyone knows the exponential form? Z is equal to exactly r e to the power I theta. Now, just like how can imaginary numbers be plotted on a real plane, how can we raise e to an imaginary power? That question still remains unanswered. Okay, that question still remains unanswered, and that will remain unanswered throughout our 12th or throughout our mathematics that we are going to study at this level. Later on, you may define it in using the power series expansions, but let's just remember it. Okay, e raised to I theta is cos theta plus I sin theta. That is called Euler's identity or Euler's formula. E to the power I theta is cos theta plus I sin theta. And this identity is very important now. I'm telling you, whenever we want to multiply or divide two complex numbers, if you don't want to go by the z1 z2 way, x1 plus iy1 x2 plus iy2, just do this. Okay, you will always reach the answer. Okay, this is Euler's formula. One more point, interesting point about this is that if we find the magnitude of e raised to I theta, what will it be? Modulus, it will always be 1. It will always be 1. Okay, it will always be 1. Exponential form, remember, is an extremely useful tool. Using the Euler's formula, we can prove the de Moivre's theorem in one step. We'll come to that later. Clear till this part? Any doubts or any clarifications further that you need? No? Okay. Okay, let me just see. Modulus covered, argument covered, Poisson form covered, exponential form covered. Okay. Yes. Useful properties of modulus. First, mod z is equal to 0 if and only if z is equal to 0. Except z equal to 0, no other complex number has its modulus equal to 0. Other results are quite straightforward. Mod z is equal to mod z bar equal to mod negative z equal to mod negative z bar. Okay. Third, negative of mod z is less than or equal to, the real part of z is less than or equal to mod z. Okay, let's consider the third and try to find out examples where the equality holds. Okay, can anyone tell me any complex number where negative of mod z is equal to real part of z? No, then minus 1. Real part is negative 1, mod z is 1, so that will work. Okay, and any complex number for which mod z is equal to real part of z? All positive real numbers. Okay, z belonging to r plus union 0. Well, even here we can include 0, but that won't be any, that is as good as a trivial solution. Okay, fine. What about this part? Any complex number where negative mod z is equal to imaginary part of z? Yes. Mod of that. Yeah, come on. Can I say negative I? Is that right? Yes, so all purely imaginary numbers having negative imaginary part satisfy the equality. That negative of their modulus is their imaginary part. And then what will be mod z equal to imaginary part of z? Purely imaginary numbers with positive imaginary part. Okay. Fifth, zz bar is equal to mod z squared. Okay, yeah, that is something that you people already know. X plus iy into x minus iy. Use a plus b, a minus b. It is a squared minus b squared. That is x squared plus y squared. That is under root x squared plus y squared squared. Correct? That is under root x plus y squared. Okay? Fine. Okay. Next. Mod of z1 into z2 is mod z1 into mod z2. That is, see now, if we use the exponential forms of the complex numbers, having noted that moduli of e to the power I theta 1 and e to the power I theta 2 are equal to 1, the first property is cleared. It will be r1 r2 into mod of e to the power I theta 1 plus theta 2. Now, no matter what theta 1 and theta 2 are, cos squared theta 1 plus theta 2 plus sin squared theta 1 plus theta 2 is always going to be 1. So that always makes the thing. Okay? Sorry, z1 into z2, z1 into z2. And same thing also applies with division. right? Same thing also applies with division. Okay, is that clear? Okay, let me write it here. Z1 by Z2 equals R1 by R2 modulus of e to the power I theta 1 minus theta 2. Use the laws of indices. So what will happen? R1 by R2, that will remain there. E to the power I theta 1 minus theta 2, no matter what that is. Mod of that is always going to be 1 due to cos squared theta plus sin squared theta equal to 1. Is that clear? Okay. Z1 plus Z2 mod squared is mod Z1 squared plus mod Z2 squared plus Z1 bar Z2 plus Z1 Z2 bar. You may verify these results at home. You can also try proving them. They are very simple. If you want, you can prove them. See, now what I'm saying is, it's not absolutely essential to know the results. Okay, first two are trivial, you can remember them. But for the third one and the fourth one, you just take a look at them and see how they have been derived. Okay, everything else will basically come to you pretty easy. Okay, I'm not saying you memorize them. If you like to memorize them, you can, but that's not a mandatory requirement, at least for this exam. Okay. Second, mod of Z1 minus Z2 squared is mod Z1 squared plus mod Z2 squared minus Z1 bar Z2 minus Z1 Z2 bar. Okay, you can prove them by assuming Z1 as x1 plus I by 1 and x2 as Z2 as x2 minus I by 2. You can take examples and verify. Last one, that is important, that is called triangle inequality. Okay, that is called triangle inequality. Okay, which says mod of the addition is always less than or equal to addition of the mods. Mod of Z1 plus Z2 is always less than or equal to mod Z1 plus mod Z2. Okay, so you know this, right? You already know this, but can you tell me what conditions should Z1 plus Z2 satisfy such that mod of Z1 plus Z2 becomes equal to mod Z1 plus mod Z2? Can you identify the condition? Yes, please. Can you identify the condition for this? When can we have mod of Z1 plus Z2 equal to mod Z1 plus mod Z2? Anyone? The condition is when 0, Z1 and Z2 are collinear. Got it? Okay, when 0, Z1, Z2 are collinear. Okay, and okay, see, let's do this. Look here. There are two possibilities here. Okay, there are two possibilities here. Suppose this is the line. Okay, suppose this is the line. Suppose origin is here, Z1 is here, and Z2 is here. Then clearly mod of Z1 plus Z2 is going to be mod of Z1 plus mod of Z2, because essentially this segment, when you start from here, that will get stretched. Okay, if they are on the other side of origin, okay, they are on the other side of origin, let us say Z1 prime and Z2 prime, even then that equality will get satisfied. Okay, now I want to ask you a question. will that equality be satisfied if origin lies in between the two complex numbers? If that's the case, does the equality satisfy, or is it satisfied? No. For example, if z1 prime is negative of z1, then it will be 0, but none of the mods are 0. Okay, so when 0, z1, z2 are collinear and origin divides segment joining z1 and z2 externally. Do you get what I'm saying? Yes, that is important. Okay, fine. That is called triangle inequality. Okay, useful properties of arguments. Now, I'm not going to verify them again, but I just want to tell you one thing. See, suppose you find z1 in its exponential form, and suppose you find z2 in its exponential form. Okay, and it turns out that both θ1 and θ2, they are greater than pi by 2. Or even equal to pi, that's fine. Okay. But when you add them, like z1 plus z1 into z2, for the product the arguments get added. Now what will happen to θ1 plus θ2? It's fine if it is equal to pi, but it will actually be in between theta, in between 2 pi and pi. Now see, the moment it exceeds this, okay, let's exclude pi just for the sake of it. Okay. So here what do you find? This is exceeding the range of, this exceeds the range of principal argument. Okay, this exceeds the range of principal argument, and therefore what we do is we say plus 2k pi. So we can always subtract 2 pi or add 2 pi or a multiple of that to get that in the principal argument range, and hence we add 2k pi here. Argument of z1 plus argument of z2 plus 2k pi. See, that's what I wrote here. That is what I wrote here. Yeah. See, look, z1 into z2 is mod r1 r2 into mod e to the power I θ1 plus θ2. That's fine. Whatever value you have for θ1 plus θ2 or even θ1 minus θ2, we don't care. Okay, we don't care. So it is correct to remember that argument of the product is addition of the arguments, pretty similar to the rules of logarithm, that log of AB is log A plus log B. Okay, but here there is something else attached to it, and what is that? 2k pi. Do you realize that? Okay, do you realize that? Yes, k should be an integer. Okay, k should be an integer. Argument of z bar is negative argument of z, but that's pretty clear. Same thing, argument of z1 upon z2 is arg z1 minus arg z2 plus 2k pi. And please note the striking resemblance between these two and laws of logarithms. Because after all, both have an exponential connection, isn't it? Both have an exponential connection. Okay? So, pretty useful connection. Fine. Okay, now the other two results are also important. Well, you can come up with as many results as you want, but just for demonstration, illustration, we have taken these two. When we have mod of z1 plus z2 equal to mod of z1 minus z2, okay, that is a biconditional of argument of z1 minus argument of z2 is equal to pi by 2. Okay, and secondly, mod of z1 plus z2 equal to mod of z1 plus mod of z2 implies, or even only, argument of z1 is equal to argument of See, this is what we typically do for positive numbers or even negative numbers, but real. Okay, positive or negative numbers, or if they are on the same line. Okay, collinear. Okay, collinear complex numbers. Just wait. Mod of Z1 plus Z2 is equal to mod Z1 plus mod Z2. Will that always work? Mod of Z1 plus Z2 is equal to mod Z1 plus. Okay, I am a bit doubtful about this. Let's take Z1 as 2 plus 3i. And let's take. Oh, okay, fine. We are. Yeah, that's right. Collinear complex numbers, and they will always be on the same side because argument can be. See, look here. If I draw a line like this, okay, if I draw a line like this, then all complex numbers lying in the third quadrant, their argument is same, and that is negative octaves. Okay, and all points on the same line in the first quadrant, okay, they have what? They have positive and acute modulus. Okay, yeah, okay, that's fine. Mod of Z1 plus Z2 is mod Z1 plus mod Z2 implies, and is applied by argument of Z1 equal to argument of Z2. But for the first, mod of Z1 plus Z2 equal to mod of Z1 minus Z2 implies that they are perpendicular. Now, how are we going to verify that? Okay, how are we going to verify that? We can use the analogy of two perpendicular vectors. Okay, we can use the analogy of two perpendicular vectors. Look, this vector and this vector have the same resultant, and this vector and the vector below will have the same resultant in two dimensions, right? Well, it will not have same resultant, but their magnitudes will be same. Their mods will be same. Okay, so when mod of Z1 plus Z2 is equal to mod of Z1 minus Z2, they should differ by, their arguments should differ by 90 degrees. Is that clear, or shall we take some examples to demonstrate that? Yeah, others? Understood? Aishwarya, did you understand? Clear. Okay. Yes. Now let's go to De Moivre's theorem. Let us go to De Moivre's theorem. The theorem tells us that cos theta plus I sin theta raised to n, okay, raised to n is equal to cos of n theta plus I into sine of n theta. Okay, I into sine of n theta. Okay, we can prove this using the Euler's formula in two steps. Use this as e raised to I theta raised to n, and then we can write as e raised to I n theta, and then again use Euler's formula for n theta. The proof is pretty simple. Okay, the proof is pretty simple. That's the proof. Okay, we can also prove this by mathematical induction, mind you. Okay, we can also prove this by mathematical induction. Proof methods 2. 1. Mathematical induction. We have to use binomial theorem there. Okay, using binomial theorem. But see, now when we decide to prove it using mathematical induction, we have to restrict n to the set of natural numbers. Okay, but when it comes to proving by Euler's formula, we may take any real number. Okay, we may take any real number. Okay, Now, what are the uses of de Moivre's theorem? Using de Moivre's theorem, we can prove many trigonometric formulae. Okay. Now, usually we know till cos 3 theta. Okay, we usually know till cos 3 theta. So let us try to find the formulae for cos 4 theta and sin 4 theta. Okay, let's try to find the formulae for cos 4 theta and sin 4 theta. Then I'll come to this part, cos raised to 4 theta. Okay, look. I'm going to first consider this cos 4 theta plus I sin 4 theta. Okay, using Euler's formula, I can write it as cos theta plus I sin theta raised to 4, or using de Moivre's theorem. And now I can apply the binomial theorem. Okay, so what will it be? Cos raised to 4 theta plus 4 cos theta, 4 cos cube theta into sin theta I plus 6 cos squared theta into negative 1 into sin squared theta plus 4 cos theta into sin cube theta, but this time it will be negative iota. Okay, it will be negative I, and finally it will be sin raised to 4 theta. Now just consider the real parts. You have a ready-made formula for cos raised to 4 theta. Okay, you have a ready-made formula for cos 4 theta. It will be cos raised to 4 theta minus 6 cos squared theta into sin squared theta plus sin raised to 4 theta. If you want, you may write sin squared theta as 1 minus cos squared theta and get an expression only in terms of powers of cos theta. Okay, you can try that as homework. Put sin squared theta equal to 1 minus cos squared theta and get cos 4 theta. Get cos 4 theta in terms of powers of cos theta. Will you be able to do that? Yes. Okay. And if we equate the imaginary parts, then you will have a formula for sin 4 theta. Now for that you can replace cos, well, what will you do with cos cube then? Sin 3 theta is 3 sin theta minus 4 sin cube theta. Okay. And you have to come up with one way or the other to take cos theta and replace it by root of 1 minus sin squared theta. Hopefully that root will get eliminated. You can try that. Okay, you can try that. Fine. Let's verify that. Let's verify that once. Maybe I should do it for cos 4. Cos 4x. Okay. And let's do it for this one. Okay. Right. Okay. Fourth power of cos x. Yeah, fourth power of cos x minus 6 into cos x squared sin x squared plus fourth power of sin x. See, both things match very well. Okay, this is cos 4x. Bring this in, it overlay, the blue curve overlaps. Oh, sorry. Yeah, the blue curve overlaps with the red curve. Okay, the blue curve overlaps with the red curve. So the formula for cos 4 theta in terms of powers of cos theta is correct. Okay, fine. Now, can you tell me a way to find fourth power of cos theta in terms of multiples of theta? Any suggestions for cos raised to 4 theta? See, what did we do? Here we found out the fourth multiple of theta in terms of powers of theta, cos theta. Now my question is, can we find the fourth power of cos theta in terms of theta, 2 theta, 3 theta and 4 theta? If yes, how can we do that? Okay. Yes. We can do, sorry. Yeah, okay. See, we can use these formulae which we have revised long ago, or which we have seen long ago rather. Remember? Yeah, those are the formulae that are important. Cos theta is e raised to I theta plus e raised to negative I theta by 2. Sin theta is e to the power I theta minus e to the power negative I theta upon 2i. That I should not be forgotten. That's I, okay? Not just 2. For cos it's fine, but for sin theta we have to divide by I, because that we get actually 2i sin theta. Okay, 2i sin theta is what we get. Fine. So for cos 4 theta we can take the help of this expansion here, expression here. E to the power I theta plus e to the power negative I theta upon 2 raised to 4. Is that clear? Okay. So it will be 1 upon 16 into bracket. 1 upon 16 into bracket. Acha, what will be there? First of all, e to the power I theta. So fourth power of e to the power I theta, e to the power I for theta plus 4 into e to the power I theta's cubed, and first power of e to the power negative I theta, so 3 minus 1, so that will be 2 theta. Okay, that will be 2 theta. Okay, then it will be 4c2, which is 6. 4c2 is 6. E to the power I square of that and square of that, so that will be 0 theta. And the fourth term will be 4 e to the power I, only first power, but a cube of e to the power negative I theta. Okay, so that will be negative 3 equal to negative 2. And okay, let me just shift this a bit to its left so that I can accommodate all the terms in one at one horizontal level. Okay, yes. And what will be the last term? E to the power I negative 4 theta. Has everybody understood this? Okay. Now look, let's again use the same formula. What I'm going to do is I'm going to combine these two terms. Which two terms? First and the last. Okay, let me use different colors. E raised to I 4 theta plus e raised to I negative 4 theta. Will that not be equal to 2 cos 4 theta? Look here, 2 cos 4 theta. 2 cos 4 theta. Okay, now collect second, which is e to the power I 2 theta, and fourth, which is e to the power I negative 2 theta. Okay, so what will that be? That will be 4 into 2 times cos 2 theta. Yes, no? Understood? Did understand? Understood. And e to the power I 0, that's 1. So fix it. So we now got a formula which we are not expecting for cos 4 theta. Now who knows, they might ask you third term, fourth term or coefficient of something in cos 37 theta, who knows. So that will be a nice question of combination of binomial theorem and this. Okay, isn't that nice? Cos 4 theta equal to cos 4 theta by 8 plus cos 2 theta by 2 plus 3 by 8. That's the formula for cos 4 theta. Understood? So you may take this possible question. coefficient of, let's say, cos m theta in expansion of cos n theta n greater than b. Okay, now let's see if that's right. Should be right. Let's verify. Okay, cos 4 theta's graph. Okay, that's ready. Oh, sorry. I think I made a mistake. It's cos raised to 4 theta. Sorry. Cos raised to 4 theta. Cos raised to 4 theta. But I'm saying okay, cos raised to n. Okay, yes. Okay, let me delete this. This is 4th power of cos x. Okay, this is 4th power of cos x. Okay, now let's start plotting everything. Cos of 4x upon 8 plus cos of 2x upon 2 plus 3 by 8. What do you see there? Green overlaps with red. Red, green, red, green, red, green. Then so cos raised to 4 theta is that. In later standards, you will call this Fourier series of cos raised to 4 theta. When we express any function in terms of an infinite series of multiples of sin theta and cos theta, we call it Fourier series. Okay, and that also has some useful applications in solving differential equations. Okay, understood this? De Moivre's theorem. Okay. Last part. Well, one of the applications of De Moivre's theorem, well, we saw two of them, now the third one, is to find nth root of 1. Now if we find nth root of 1, nth root of any other number can also be easily calculated. Okay, so let's go for nth root of 1. First of all, what we have to do is, we have to consider the following expansion. Okay, we know that 1 is a complex number whose modulus is 1 and argument is 0. Okay, now we will use the periodicity. We will use the periodicity of trigonometric functions. Let me put it that way. Let's use the periodicity of trigonometric functions. Okay, and let's say 2 pi k, where k is any natural number. Okay, k is any natural number. Essentially what I'm saying is this. Okay, I know that cos of theta plus 2 pi k is cos theta, and sine of theta plus 2 pi k is also sine theta. These two properties, when are combined, we get that 2 pi k form. Understood? Using De Moivre's, using the Euler's formula, cos theta plus I sine theta. Do you follow this? Okay. Now, when it comes to the nth root of 1, we basically write it as e to the power I 2 pi k by n. 2 pi k by n. Now the question is, how many values of k are we going to put? So we need to put the values of k from 0 to 1 to 2 up to n minus 1. You might ask, what happens if we put n? That again comes back to, if we put n, then that again comes back to 0. Okay, that because that is e to the power I 2. Understood? So if I take n as 3, then I'll get e to the power I 2 pi k by 3. K can take values 0, 1 and 2. Okay, 0, 1 and 2. So what will be the root when k is equal to 0? When k is equal to 0, the root is 1. When k is equal to 1, we have e to the power I 2 pi by 3, okay, which is cos 2 pi by 3 plus I sine 2 pi by 3, which is negative 1 upon 2 plus I root 3 by 2, and k is equal to 2 e to the power I 4 pi by 3, that's cos 4 pi by 3 plus I sine 4 pi by 3, that is the conjugate of this. Okay, now see, if I call this root as omega, this becomes omega squared. Okay, or if this is called omega, then this becomes omega squared. Do you know those two connections? If one of the complex cube roots of one, sorry? Yeah, no, you should verify them. Okay, that should be your homework. Verify. Omega is omega squared. Sorry, omega. Verify that if omega is, well, you can just see that here. There's no need to even verify. Look here. Suppose I squared e to the power I 2 pi by 3. Suppose I square this number. Am I not going to get e to the power I 4 pi by 3? Yes. And suppose I square e to the power I 4 pi by 3. I'll get e to the power I, what will I get? 8 pi by 3. But 8 pi by 3 is essentially 2 pi plus 2 pi by 3. Right? So that automatically gets verified. Okay? That automatically gets verified. Okay. But there is one more way of arriving. At these complex cube roots, and that is by assuming them to be z, or any one of them to be z. Okay? Suppose z cubed is equal to 1. So you then say z cube minus 1 equal to 0. Then you factorize it as z minus 1 into z squared plus z plus 1 equal to 0. This gives the real cube root, z equal to 1, and this gives us z equal to minus b plus or minus root of b squared minus 4ac upon 2a. Minus 1 upon 2 plus or minus root 3 by 2. Okay, so you can also find the cube roots of 1 by that way, but well, if we find the nth roots, then that is easier. Okay, have you understood this?
Yes, sir.
Yes? Okay. Now I'll tell you one more way, or not way actually. Sometimes, I don't think they will ask you this, but suppose you are required to find nth roots of minus 1, nth roots of I, or nth roots of negative I. Then how are you going to proceed? You're going to proceed by remembering their exponential representations. Negative 1 is e to the power I pi. I is e to the power I pi by 2. And this is e to the power I negative pi by 2. Okay, and then you can add 2 k pi there. Okay, then you can add 2 k pi and then take the nth root. Okay. E to the power I negative. Well, so this time I need to add 2k pi I. Okay. Hope you got what I'm saying. And z will be, that power will get in its denominator for z. Got it? Yes. Okay. IISER, you were from ICSC, right, or IISc? You people have this also, if I'm not wrong. You people have this in 11th complex numbers. Okay. I think I have discussed all major points that I had to discuss today. Yes. Achha, one last and then we'll stop. You might already know the answer to this question, but what is I raised to I? Ever seen this question? This is a very popular question in engineering mathematics. I raised to I, see, what you have to do is you have to write I as e to the power I pi by 2. Yeah. And then when you raise it to I, it is e to the power negative 2. So I raised to I is purely real. I raised to I is purely real. Okay? Fine. Now they may not also ask you this, but Suppose we are asked to find log of a complex number. We don't have that, but in case, log of a complex number will be converted immediately to polar form, exponential form. Okay, so it will be ln r plus ln e to the power I theta. So what will that be? Ln r plus I theta. Okay, that is the log of complex number. Okay. All right. Now you can also define one power raised to other power, one number raised to other complex number, but I think that's enough. Okay. Fine. So we have completely discussed the theory of complex numbers today. Well, there is one part that I have not covered deliberately, and that is there can be some conic sections which we can represent using complex numbers. But because we have not yet studied conic sections like straight lines, circles, ellipses, I will just put these formulae there when we discuss coordinate geometry in detail. Okay? Fine. Today we are going to revise quadratic equations. Okay? Today we are going to revise quadratic equations. So let us start with the preliminaries. Quadratic equations belong to a family of equations called polynomial equations, right? So any quadratic equation is essentially a polynomial equation, correct? It is a polynomial equation, which means by the fundamental theorem of algebra, no matter what the coefficients of quadratic equations are, we will always have roots of quadratic equations defined in the set of complex numbers, right? So any quadratic equation is a polynomial equation of degree 2. Okay, of degree 2. What is the standard formula? Ax squared plus bx plus c equal to 0, where a, b and c are complex numbers, and of course a is not equal to 0. Okay, that is the standard form, standard representation. There are a few minute details you should pay attention to. First is that we are not saying ABC belong to the set of real numbers. We are saying that ABC belong to the set of complex numbers, and the second part there, it basically follows from the definition of the quadratic equation. Okay, how? We are saying that it is a polynomial equation of degree 2. Degree 2 means the largest power of the unknown is 2, which means its coefficient can never be equal to 0. Okay, a cannot be equal to 0, otherwise it will become a linear equation, right? What are the roots of quadratic equation? Roots are basically values of x which satisfy the quadratic equation. Roots are values satisfying the equation, right? Values satisfying the quadratic equation. Can anyone tell me the formula for the roots? Negative b plus or minus root of b squared minus 4ac upon 2a. Okay, minus b plus or minus root of b squared minus 4ac upon 2a. What is the formula for the sum of the roots? Well, the root part will go, so it will be negative b by 2a, and if you do the product alpha into beta, the product will be c by a. These are some basic formulae. Okay, we can also come up with the difference formula, mod of alpha minus beta, because we do not know a priori which one of them will be greater. Okay, mod of alpha minus beta will be positive root of, which identity are we going to use? A minus b bracket squared is a plus b bracket squared minus 4ab. Okay, so it will be plus alpha plus beta bracket squared minus 4 alpha beta. Okay, so you can just remember this. You or people already know sum and the product formula of quadratic equations roots. So alpha minus beta, the difference can be very easily found out. Okay. Yes. Okay, now I just want to add one more point here. If you check the JEE syllabus or any syllabus in general of engineering competitive exams, you will find something called symmetric functions of roots. Okay, symmetric functions of roots. Now, what are these symmetric functions? By symmetric functions, they mean even if the positions of alpha and beta are interchanged, okay, even if the positions of alpha and beta are interchanged, the function doesn't change. Okay, take for example alpha by beta plus beta by alpha. Okay, alpha by beta plus beta by alpha. Now, if the positions are interchanged, then beta beta will come here and alpha will come here and here. Did it change the function? It did not. Okay, so that is an example of a symmetric function. Okay, and we can always express any symmetric function in terms of the sum and the product. Okay, yes?
The equation of sum of the roots is the minus b by
Minus u by, sorry, minus u. Sorry, minus u by, thank you. Yeah, alpha by beta plus beta by alpha is that, so that is a symmetric function, and we can always write it as alpha squared plus beta squared upon alpha beta, and again here we can use alpha plus beta bracket squared minus 2 alpha beta upon alpha beta. Okay, can you give me examples of some other symmetric functions? Sine alpha plus sine beta. Okay, sine alpha plus sine beta, well, that is also a symmetric function, and we actually have a formula for this. 2 sine alpha plus beta by 2 cos alpha minus beta by 2. Now you might ask, is it possible, how can it be alpha minus beta by 2 there? Look, okay, look here, if we change alpha to beta and beta to alpha, because cos is an even function, okay, because cos is an even function, cos of negative theta will be cos theta. It didn't change anything here, and it is also not going to change anything there, because cosine is an even function. Okay, now although we will not be dealing with symmetric functions of the second kind, sine alpha plus sine beta, because we should exclusively know alpha and beta, only then we can find them, but maybe I should have said rational functions of roots. Okay, we can always express them as in terms of the sum and the product of the roots of the quadratic equation. Okay, understood? Symmetric functions of roots.
yes.
Okay. Now in today's lecture, we will be emphasizing more on the visualization of the quadratic function, because see, the theory of the quadratic equation just ends right there. The formula for the main quadratic equation, its roots, sum of the roots and product of the roots. Okay, but despite knowing all these things, we often find ourselves in a very difficult situation, because the questions may be framed like this. What should be the relation among coefficients if the roots always lie in the open interval 1 to 2, or one root is greater than 1, the other root is less than 1, okay, something like that. And then we are stuck, because we know very well these formulae that we discussed just now, but maybe we are not used to the way of we are not used to that kind of problems whose example I just gave them. Okay, so to make ourselves used to those situations, we are going to take a look at the graph of the quadratic function, and we are also going to figure out some conditions. What do they mean in the context of the quadratic equations or functions? Okay, fine. So first of all, we make a small change. We do not say quadratic equation now, we say quadratic function. So we know it's ax squared plus bx plus c. It is no longer an equation now. So it is not equal to something. Okay, we say quadratic function f of x equal to ax squared plus bx plus c, and it's zeros. See, a function has zeros. Okay, a function has zeros, an equation has roots. A small difference, but nonetheless important. Okay, a function has zeros, an equation has roots. Okay, for example, f of z equal to 1 plus z squared has a 0 at z equal to -1 plus root 3 r by 2. Okay, and if I want to convey the same information, okay, if I want to convey the same information using equation, we will say 1 plus z squared equal to 0 has a root equal to -1 plus root 3 r. Okay, a minor change, but nonetheless it is essential to know. A function has zeros and equation has roots. Now what is meant by zero of a function? Those values whose images are 0 or which are mapped to 0 in the range of the function. Is that clear? Or should I explain it again? You understood it, right? Okay, that's something. Yeah, that's something which is a minor topic, but nonetheless you should know the terms. Okay, in which context which term is used. Okay, maybe I should put it here. Okay, a function has zeros, an equation has roots. Now here I have taken the help of the complex cube root of unity, that part, so that I was able to arrive at the equation quickly. Okay. Well, are you aware of a function called Riemann zeta function?
So, yeah, sir.
Okay, I will just tell what that function is. Okay, well, I will not tell you that function because it is a function of a complex variable, but I'll just tell you why it is significant. Okay, look, sin x equal to 0. Okay, okay, let's say sin x. Okay, let's say sin x. Sin x is a function, right? All of us agree that sin x is a function. Sin x has a 0 at pi because sin pi is 0 at x equal to 2 pi, right? And so on. That is not very interesting because we already know it. Okay, that is not as interesting as it sounds because it's something that we already know. Somebody who's looking at trigonometric functions for the first time, he or she might say, oh, okay, that's interesting. But this Riemann zeta function has some characteristics which are not yet correctly understood. Okay, a Riemann zeta function. Okay, and there is a hypothesis related to it called Riemann hypothesis, which says that all non-trivial zeros, non-trivial means non-obvious, all non-trivial zeros of zeta function have real part 1 by 2. So they're complex numbers, but the real part is 1 by 2. Always. If you prove this, you will get a prize of $1 million. I'm not joking. You just search for Riemann hypothesis on Google later. And Millennium Prize problems. Okay, you can Google, or you can also Google Clay Mathematics Institute. Okay, you can also Google Clay Mathematics Institute and you'll find this. There are 7 problems. I think only one of them has been solved. The remaining 6 are yet unsolved, and you will get a cash prize of $1 million given by that institute if you manage to prove, or no, hypothesis can be disproved or proved. Okay, it is an open question. Okay, but that is related to zeros of a function. Okay, that is related to zeros of a function. Okay, okay. Returning to quadratic function f of x equal to ax squared plus bx plus c. Although I have said earlier that the formulae that we have written here apply to complex coefficients also, a, b, c can be complex numbers. We at this level will be considering only those quadratic functions where coefficients are real numbers, a, b, c are real. Okay, so let's just make that change. For us, a, b, c belong to set of real numbers. For what? For the graphical representation, because only then we can represent them on a graph. Correct? Okay. Now, graph is always parabolic. Okay. Graph of f of x equal to ax squared plus bx plus c is always parabolic. So only 2 possibilities are there. Okay, which possibilities are there? Possibility number 1, okay, well, no need to show the vertical axis. Possibility number 1 something like this, and possibility number 2 something like this. Now see, it may intersect the x-axis, huh? This. If it intersects the x-axis, either it will touch the x-axis, in which case it will have equal roots. If it intersects x-axis at 2 different points, 2 distinct points, we say it has distinct or unequal roots. Okay, and if it doesn't, then we say that the graph has imaginary roots. Okay, the function. Okay, okay, or we must say zeros. Case 1. Suppose our discriminant d is negative. Okay, suppose our discriminant d is negative. This condition that d is negative, this is the condition for which roots? Complex roots. Correct? This is the condition for complex roots, because that's the term that sits inside the root here, discordant squares. Okay. Now if we have complex roots, or if the discriminant is negative, the graph is never going to meet x-axis, right? Because the moment the graph of the function meets the x-axis, we can say that it has zeros, which are real numbers, right? Okay. Now this condition, a greater than 0, what does that mean? A greater than 0 means the graph is always above x-axis. Okay, the graph is always above x-axis. Okay, the graph is always above x-axis. Now, can you tell me how can you prove that when a is greater than 0, the graph is always above x-axis with that condition? My question is, suppose it is known that the discriminant is negative and a is positive. How can we prove that the graph is like this and not like this or like this? Can you answer that question? It's easy. You just find the limit as x tends to plus or minus infinity of f of x. If this limit is infinity, see, because, okay, look, when we have a polynomial function, Okay, when we have a polynomial function, then the largest power of x is always going to dominate the remaining powers. Okay, the largest power of x is always going to dominate here the other powers, and it always happens, okay, for polynomials specifically, as x takes larger and larger values in magnitude. So positive infinity or negative infinity tending to. And but then you ask this question, oh okay, so the behavior of this function near or for larger values of x in magnitude, the function's behavior is totally decided by the sign, whether it is going to positive infinity or whether it is going to negative infinity, right? And when a is positive, this limit is infinity. And that's why you have to conclude that it has to be like a U shape and not an inverted U shape. Because if it were an inverted U, then a would be negative, right? Then a would be negative. X squared always positive, so negative of that will be, it will give us larger and larger values of magnitude, but they will have opposite sign. Have you understood this argument?
Yes, sir.
Okay. Okay. Now let us take the similar argument. Okay, let's take up a similar argument, and here I'll say because we have a negative discriminant, we say that the roots are complex. But what does it mean in the context of the graph of the function? It means the graph is never going to meet x-axis. Why? Because if the graph of this function were to meet the x-axis, it would mean that the zeros of that function or the roots of that quadratic equation are real numbers, but that's not going to happen because b squared minus 4ac is negative. Okay, fine. And then for a greater than 0, it was above x-axis. Now a less than 0, it is below x-axis. Okay, well, sorry, I just changed the color scheme. Let me be more consistent. Okay, so complex roots here, and this is going to be below x-axis. Okay, below x-axis. Now if you know a bit of calculus, okay, then you can also arrive at the result regarding the maximum and the minimum value of the function. Okay, how to arrive at that result? It's very clear. Go to the function, and differentiate it. You will get 2ax plus b. Okay, first derivative test tells us that whenever derivative is 0, we have a local minimum or maximum or, well, inflection point. So x is equal to negative b by 2a. That is an inflection point. Well, we say it's a stationary point. Okay. Now if we take the second derivative here of the function, it will just be 2a. It's a constant. Okay, f double dash of x is 2a. The second derivative test tells us that when a is positive, we have a local minimum there, and that's the case with this a positive. See that? And when a is negative, we have a local maximum there, and that's this point. Did you get that?
Yes, sir.
Yeah, so knowing calculus helps us better understand all these conclusions which we perhaps study before our introduction to calculus. Okay, this is first derivative test, and this is second derivative test. Okay, this is second derivative test. Okay. Now, third condition is this. Suppose the discriminant is positive. Okay, suppose the discriminant is positive. What does it mean? It means our quadratic equation has real roots. Okay, our quadratic equation has real roots. And if I say that a is still greater than 0, if I say that a is still greater than 0, the shape of the graph is still like this. Okay, fine, and that's the exact. That's the third possibility. Okay, and it is interesting to note here that alpha and beta, okay, alpha and beta will be equidistant from this point. Alpha and beta will be equidistant from this point. So if I call this length as L1 and this length as L2, L1 has to be equal to L2, and even the quadratic formula tells us the same thing. How? If alpha becomes negative b upon 2a plus root of b squared minus 4ac upon 2a, then beta becomes what? Negative b by 2a minus root of b squared minus 4ac upon 2a. Understood? So the roots are equidistant from the, I would say, the midpoint, that is negative b by 2a. Or we may also get this result that alpha plus beta by 2, the arithmetic mean, is actually negative b by. We already know it. Wait. Negative b by a. Wait. Alpha plus beta is negative b by a. Yeah, negative b by 2. Correct. Negative. Okay. Yes. Alpha plus beta is negative b by a at 1. Yeah. Okay. So that point acts as the midpoint. Okay. Now we can also have a situation where this graph is inverted like this. Okay. So let's discuss that situation. But here we can also write specifically for this figure that f of negative b by 2a is negative. Okay, f of negative b by 2a is negative, only then the graph as shown in this figure will be there. Otherwise it will not be there like that. Okay, this is the mirror image of that, you can say. This is the mirror image of that on x-axis. So here also the discriminant is positive, indicating that the roots are real. Okay, real roots. But because a is negative, okay, because a is negative, what will be the shape of the graph? The shape of the graph will be inverted U. Okay, the shape will be inverted U, and this time again we can conclude that these two roots are equidistant from negative b by 2. I will not repeat that exercise again. Okay, L1 will be equal to L2 even for this case. And what can we say about the sign of f of negative b by 2a in this case? It will be positive. Do you follow this? In the previous case it was negative, obviously. Followed? Understood?
Yes, sir.
Okay. Yeah. Now, let us try to interpret this geometrically. Suppose we are given a condition for roots of the quadratic equation that these roots should always be positive. Roots should always be greater than a given real number k. Okay, the roots should always be greater than the given real number k. Okay, now we will be discussing two possibilities. Okay, first suppose we take the graph of u. Okay, the graph of u automatically means two things. First is a greater than 0. Right, first it means a greater than 0, and second d greater than 0, because when we say roots greater than k is a real number, we are automatically saying that the roots are real. So graphs must intersect the x-axis. Okay, a greater than 0, d greater than 0. When I say that roots are greater, k has to be to the left of the smaller of the two roots, which automatically means that k should be to the left of the midpoint of alpha beta segment. So negative b by 2a. So that is our second condition. K is less than negative b by 2a. And specifically for this graph, we have to say that f of k is positive. Do you agree? F of k positive, f of k positive. Secondly, k should be smaller than negative b by 2a. Is that clear? Yes. Now you can easily arrive at these conditions based on the given quadratic function or equation. But this is just to make you realize that drawing a graph and knowing how the value of a and the value of the discriminant b squared minus 4ac decides the shape of the quadratic functions graph. Okay, now let's discuss the inverted U case. In the inverted U case, you have to realize that discriminant has to be positive, otherwise the roots will not be real. But in this case, a should be negative. Okay, a should be negative. Again, for alpha and beta to be greater than k, we should have k to be less than negative b by 2a, or it should be to the left of alpha and beta, and therefore it has to be to the left of negative b by 2a also. Okay, and this time, because a being negative, we have the condition f of k should be negative. Okay, f of k should be negative. Now if you observe the two conditions here carefully, d greater than 0, d greater than 0, k less than negative b by 2a, k less than negative b by 2a, only the third condition is different. In the first we say f of k is positive, in the second we say f of k is negative. So we can say that the net condition is this, overall condition. For what? Overall condition for roots greater than k. The overall condition is this. Look, d has to be positive, of course, because we want the roots over here. K has to be less than negative b by 2a, obviously. And now, if we take the product of a and f of k, look, in the first case, a greater than 0, f of k greater than 0, so the product has to be positive. In the second case, a less than 0, f of k less than 0, so the again product will become positive. Yes, so we can combine that and put this. That's the overall condition for roots to be greater than k. Have you understood this?
Yes.
Yes? Can you people find out the condition for roots to be less than k greater belonging to the set of real numbers? Yes?
Yes, sir.
Roots, remember, roots will again be real. So d greater than 0, that condition has to be there. Okay? Look, I'll just draw the sketches for you. You just develop the inequalities on your own. Okay? Okay. Okay, so please try that. This is a positive, this is a negative. Okay, you can, well, I'm sure you will be able to develop the conditions pretty easily. Okay? Okay. Yeah. Now, suppose we are given this condition that roots are real, but one of them is greater than k and the other one is less than k. Okay, one of them is greater than k and the other one is less than k. Again, we will consider two situations. Situation number 1, a greater than 0. Situation number 2, a less than 0. A greater than 0 implies the graph is like this. A less than 0 implies the graph is like this. Okay, is that clear?
Yes, sir.
हाँ. Now, b squared minus 4ac greater than 0 is the common condition. Okay, it is the common condition. But now we have to realize this. What is that? When a is negative, or rather let's start with the first. When a is positive, automatically f of k becomes negative, and if a is negative, then f of k becomes positive. So the combined condition can be said as the product a into f of k is always negative, because one thing being or having opposite sign, okay, but one thing having opposite sign to that of the other. A greater than 0, f of k less than 0, a less than 0, f of k greater than 0. So the combined condition is a into f of k less than 0. Is that clear? Yes. Okay. Now we can complicate things here. We can complicate things here and develop conditions for alpha less than k less than negative b by 2a, alpha less than negative, okay, less than beta of course, alpha less than negative b by 2a less than k less than beta. Okay, we may think about, well, you can start thinking on the lines of derivatives sign there. Okay, in the first case the derivative is what? In the first case here, a greater than 0 if you want it. For a greater than 0, can I say that f dash of k is negative? And for a greater than 0 second case, I can say that f dash of k is positive. Do you agree? And for a less than 0, here we must have f dash of k what? Positive. And here we must have, for a less than 0, f dash of k should be negative. Got it? Yes?
Yes.
Okay. Yeah, now we can come up with as many situations as we want. Here are some standard situations. The next condition is for exactly one root lying in the open interval k1, k2, where k1, k2 are real numbers. Okay, fine. Now we can collectively come up with a condition here. Okay, we can collectively come up with a condition here. Look, suppose only one root lies. Only one root lies in that interval. Look here. So the sequence has to be k1 less than alpha less than k2. What does that mean? That means f of k1 and f of k2 will have opposite signs. F of k1 and f of k2 will have opposite signs, right? Or we can also say exactly one. So k1 less than beta less than k2. It means f of k1 into f of k2 should be negative. Is that clear? Is that clear? Same thing applies to the other graph also. Irrespective of the value of a or the sign of a, f of k1 and f of k2, if the function is evaluated at that particular point or points, the product of the values of the function should always be negative. Make sense? Yes?
Yes.
Now actually this particular discussion can also be extended to any polynomial equation. Okay? Generalization. If f of x is a polynomial, such that f of k1 and f of k2 are of opposite signs. okay, are of opposite signs, then f of x has at least one root in open interval k1 k2, okay, because of intermediate value theorem. Do you understand that? Intermediate value theorem
Yes, sir.
applies to continuous functions. Polynomials are continuous. Okay, so yeah, you can extend it to any other polynomial function. Okay, fine. Next part. Yeah. Condition for both the roots lying in the open interval k1 k2, where k1 and k2 are real numbers. Now what does that mean? That means basically the u portion of the graph should be entirely in the open interval k1 to k2. Okay, k1 to k2 for a greater than 0. Okay, for a greater than 0, let's see the conditions. Okay, for a greater than 0, obviously the discriminant has to be positive because we want the roots to be real. So this condition is by default there. Okay, fine. Now this negative b by 2a point has to be not necessarily the midpoint, but it has to be in the interval k1 to k2. Otherwise, both roots will not be there. See, now this is a necessary condition but not a sufficient condition. Okay, second condition here is a necessary condition. This is a necessary condition but not sufficient condition. Can you tell me why? Look, suppose k1 is here. Condition is met, but alpha lies to the left of that. Okay, alpha lies to the left of that. Okay, suppose k1 is here. Or rather, okay, let me do it in this way. Suppose k2 is here. K2 is here, not k1, sorry, k2. K2 is there. So again, negative b by 2a lies between k1 and k2, but beta lies outside. So it's a necessary condition but not sufficient. Okay, what will make it sufficient? The third condition. F of k1 and f of k2 should always be positive. F of k1 and f of k2 should always be positive. Graphically, it means that this and this point. Now in this figure they have shown that these are at the same elevation, but that's not always the case. Okay, f of k1 and f of k2, the actual values do not matter, their signs matter. They should be positive. Okay, now we can similarly have the inverted condition. Okay, the inverted condition, what is going to happen here? A is less than 0, so the only change is first two conditions are there, and again we have to note that it's a necessary condition. K1 and K2, that interval contains negative b by 2a. This is a necessary condition again, but no, it's not sufficient. Because if that condition is not met, then definitely the requirement is not satisfied. But if that condition is met, it's not necessary that the condition will always be satisfied. Okay, fine. In this case, we have f of k1 and f of k2 to be negative. Again, we can see that from the graph. Conclusion we can draw that f of k1 and f of k2 should be of same sign. And additionally, what? Additionally, d should be positive, that's there, and k1 less than negative b by 2 less than k2. Okay, that's the condition for both roots in the interval k1 k2. Is that clear?
Yes, sir.
Okay. Did you guys know these things or?
Not systematically like that.
Okay, fine. Yeah, that's what I'm saying. That's what I'm saying. There can be other situations also. Okay, there can be other situations also. But the thing is, if you know that such situations exist, or if you are familiar to them, then it becomes handy for your exam perspective. Okay. Just a second. Let me have some water. Uh, you may be asked to determine the range of a quadratic rational function whose general form is this. Okay, whose general form is this. Specifically, p should not be equal to 0. Okay, p should not be equal to 0. Now, before we answer the range question, let us answer the domain question first. Okay, so the domain of this function is what? Domain is equal to the set of real numbers minus those values of x for which px squared plus qx plus r is equal to 0. Is that clear?
Yes, sir.
It is interesting to note here that limit of y as x tends to plus or minus infinity is a by p. Is there any doubt? In the limit answer? Yes or no? Understood? Or shall I explain it again?
Can explain again?
Yes. See, look. Explanation of 2. Suppose the limit is to be evaluated. Now I'll explain the positive infinity case. The negative infinity case can also be similarly explained. And just like 0 by 0 is an indeterminate form, infinity by infinity is also an indeterminate form. Okay, infinity by infinity. So L'Hospital's rule applies. Okay, L'Hospital's rule applies. So it will be derivative of the numerator upon derivative of the denominator. Okay, again L'Hospital rule applies. So it will be the derivative of the numerator upon derivative of the denominator, and that's a by. Understood?
Yes, sir.
Later on we will see that using Desmos, that irrespective of the values of b and c and q and r, the limits will always be y equal to a upon p. So this line is often called an asymptote because the distance between the curve and the line goes on decreasing. Okay, but well, we will see what that is. Fine. Okay. Now, how can we determine the range of this quadratic rational function? Okay, the range problem is very easy to be answered. What we do is we call that function as y. Okay, we call that function as y, and we now argue like this. Let's take that example and demonstrate. Let me demonstrate that for you. Okay, look. Suppose we take this function, and the objective is to determine the range of this particular function. Okay, range of this particular function. We can follow the calculus approach. There is nothing wrong there, in which we will be finding the maximum and the minimum, I would say, the values. But for that, we are first required to differentiate the function twice, which in itself is a very difficult job, especially for a rational function like this, especially the second derivative part, and then finding the roots of the first derivative equation, substituting them in the second derivative equation, and looking for the signs of the second derivative, positive or negative. Well, that is a bit time consuming. So we take this alternate approach. Okay, so x squared minus 2x plus 3 upon x squared minus 2x minus 8 is equal to y. Now what we say is, we say this. Let us rearrange it like this. Yx squared minus 2yx minus 8y. So what did I do? I took this term to RHS. Okay, so it became yx squared minus 2yx minus 8. Okay, now bring everything to LHS. Bring everything to LHS. So what will we have? We will have 1 minus y into x squared. Okay, 1 minus y into x squared Then for x, what do we have? Negative 2 plus 2y. And then for the constant term, we have 3 plus 8y. Is that clear?
Yes, sir.
Okay, this is equal to 0. This is equal to 0. Now, do you agree that this particular equation should be satisfied for all values of x? Right, because look at this. Look at, except perhaps when the denominator is equal to 0, but that's not going to stop us from saying that this particular equation here applies to all values of x. Okay, this equation applies to all values of x. Do you agree to this? Okay, fine. So if that equation applies to all values of x except for the values where we do not belong to the domain of the original function, but well, we can just remove those values later if we want, or rather if there is indeed any such value. Okay? Okay. Let me add that here, except denominator of x equal to 0 of the original function. Okay. Now if it applies to all values of x, I have to say that the quadratic equation's discriminant has to be positive. Therefore, negative 2 plus 2y squared minus 4 into 1 minus y into 3 plus 8y should be greater than or equal to 0. Is that clear?
Sir.
B squared minus 4ac should be greater than or equal to 0. Okay, simplify. 4 plus 4y squared minus 8y. Okay. Now look, 1 into 3 is 3. It is accompanied by negative 4, so negative 12. 1 into 8 is 8y is 8y minus 4, so negative 32y. Negative y into 3 is a negative 3y into negative 4 is plus 12y. Right? Then negative y into 8y is negative 8y squared into negative 4 is plus 32y squared greater than or equal to 0. Okay, now let us simplify this. 32y squared plus 4y squared will give us 36y squared. Then negative 8y minus 32y make it negative 40y plus 12y make it negative 28y. Negative 28y. Okay, negative 28y. Okay, what are the constant terms now? 4 minus 12, so negative 8 greater than or equal to 0. Divide by 4, 9y squared. Therefore, 9y squared minus 7y minus 2 greater than or equal to 0. Okay, fine. Now let's see what happens. We can factorize this. 9y squared minus 9y plus 2y minus 2 greater than or equal to 0. 9y common, y minus 1 plus 2 common, y minus 1 greater than or equal to 0. Therefore 9y plus 2, y minus 1 greater than or equal to 0. Okay, now look here. For both for the product to be positive, okay, see, when y is equal to 1, this side positive, this side negative. Okay. And then for 9y plus 2 equal to 0, aren't we going to get negative 2y by 9? Yes, negative 2y by 9, right? So when y is equal to negative 2 by 9, it is 0. When it is to the right, it will be positive. When it is to the left, it will be negative. Do you get this?
Yes, sir.
Okay. Now when y is greater than or equal to 1, or y is less than or equal to negative 2 by 9, okay, the roots are real. What does that imply? That implies that a range should be negative infinity to negative 2 by 9 union 1 to infinity. Okay. Now we are still not sure about whether these intervals are closed or open. Okay, whether these intervals are closed or open, and we can answer that only by considering okay, wait, can we answer that question? Maybe by considering the roots of the denominator x squared minus 2x minus 8. Okay, x squared minus 2x minus 8. Okay, so when we equate this to 1, okay, when we equate this to 1, okay, what are we going to get? Squared minus 2x minus 7 equal to 0, right?
No, sir. Yes, no.
Sorry, no. Wait, negative infinity till, like, okay, let's try to interpret what if that is equal to 0. Okay, if that is equal to 0, no, that's okay. Is it giving us a real root? That's what I need to check. Okay, what is that? B squared is 4 minus 4ac. No, it is actually giving us a positive root. And what if x squared minus 2x minus 8 is equal to negative 2 by 9 plus 2 by 9? Negative 7. No, but b squared minus 4ac will still be positive because that. Okay, let's see the graph of this function and try to figure out what happens. Acha, okay, wait. What we will do is we'll try to find the roots of the denominator, that x squared minus 2x minus 8. Okay, let's try to find the roots of that equation. Let's try to determine the roots of that equation. Okay, x squared minus 2x minus 8 b squared, okay, minus b, so 2 plus or minus root of b squared minus 4ac upon 2. So 1 plus or minus okay, 1 plus or minus 6 by 2. So the roots are oh sorry, they should be 2, sorry, they should be 2. 4 or 2 minus 6 is negative, or so that's negative. Okay, so at these things the function is not defined. Okay, but this stage the function is not defined. Okay, so this is -2 and this is 4. Okay, let's just see the graph and conclude from that. So our query is we are still not able to resolve whether the interval is closed or open, right? Okay, let's go to the function. X squared minus 2x plus 3 upon x squared minus 2x minus 8. Squared minus 2x plus 3 upon x squared minus 2x plus 8. Oh, minus 8. Okay, fine. Now, what was our limit? A by b. So y equal to 1, that is one asymptote, right? Y equal to 1, that is one asymptote. So 1 definitely does not belong to that range, isn't it? Yeah, okay, 1 does not belong to that. Okay, so the asymptotic range should be, well, we should have concluded that limit when x tends to plus or minus infinity, only there the limit is there. Otherwise, so 1 should be excluded. Okay, we can now answer that question by saying, because the limit of the quadratic function as x tends to plus or minus infinity is 1, it's well, that will not belong to the range. Okay, but what about negative 2.9? Does that belong to? I think yes. Yeah, okay, that does belong to the interval, right? Okay, so in conclusion, we can say the following. As limit as x tends to plus or minus infinity y is 1, 1 does not belong to range. Okay, yeah, I think we can make use of that, which we stated earlier, but we did not realize that we can make use of that. Limit as x tends to plus or minus infinity y is equal to a by p. So that a by p value should be excluded and this should be included. Okay, so this is closed and this is open. Is that clear now?
Yes, sir.
Okay, fine. So that is regarding the range of quadratic rational function. Also remember the second point here, the limit part. Take it? Okay. Now sometimes we are required to apply the condition for the common root. We will be given two quadratic equations and we will be required to find out the relation among them for the equations to have one common root. Okay, now you need not remember the equation there, but you should remember the condition. Okay, how that common root condition is satisfied. Okay, we solve both equations simultaneously. Okay, we solve both equations simultaneously to get two equations in X. Okay, the first equation can be obtained. By multiplying this by a prime and this by a and subtracting. So if we subtract, we will get a prime b minus ab prime x plus a prime c minus ac prime equal to 0, and the second equation can be obtained by multiplying this by b prime, this by p and subtracting. So that gives us ab prime minus a prime b x squared plus b prime c minus b c prime equal to 0. Okay, and then for this common part we can say that x squared's value here is actually negative of b prime c minus b c prime upon a b prime minus a prime b from second equation, no? From second equation. And the value of x squared from the first equation will be how much? Okay, negative of a prime c minus a c prime upon a prime b minus a b prime the whole square. Understood? The value of x squared from first equation. And then you can equate the two to get the required condition there. Do you follow this or not? Yes or no?
Yes, sir.
You do follow it, otherwise you let me know. I'll explain it again. Okay. See, this negative sign can be used to change the sign of this, and then one thing will get cancelled there. Okay, this and this, and then you can just come up with that condition that you see here. But no need to memorize this condition. Who will memorize that? Just remember what we are supposed to do. Okay, get the expressions for x and x squared. For square the expression for x equated with the other expression for x squared. Okay, that's the condition for common. Okay. Now, may not be very much relevant, but similar to a quadratic equation, we can also, I would say, land up in a situation where we have a cubic equation's roots. So the standard form is ax cubed plus bx squared plus cx plus t equal to 0, but surprisingly, no simple formula exists. No simple formula exists for calculating alpha, beta, gamma directly. Okay, but the conditions or the relations involving coefficients and roots can be obtained. They can be generalized. First condition is sum is negative b by a if the polynomial is ax plus bx squared plus cx plus t. That's the sum condition. And the product condition is negative d by a. Okay, so this sign keeps on alternating. Negative, positive, and negative. And the denominator is always the coefficient of the highest degree term. Well, we know it is not equal to 0, so somehow that has to be reflected, and that is reflected in the presence of that term in the denominator. Okay. Then for the first it is b, for the second it is c, and for the third it is t. Okay. Now look here. Suppose I have to form a cubic equation whose roots are alpha 2, beta 3, and gamma 4. I can directly frame it from this. Okay. How? It is x cubed minus the sum of the roots 9x squared plus product of the roots taken 2 at a time, 3 into 2 6, 4 into 3 12, 2 into 4 8, so 26x, and then minus product of the roots. Okay, minus 24. Now this is always easier because it's like differentiating. Okay, you just have everything ready and you put them and do the trick. Even if you did not know that, if you expand x minus 2 into x minus 3 and then multiply it by x minus 4, you'll get the same. Okay, now let's cross check it by solving it here. Okay, matrix equation, cubic polynomial. Yeah, so the coefficients are 1, negative 9, 26 and negative 24. Oh, sorry, negative 24. Not. Oh, sorry. Did I make any mistake in that? No. Oh, okay. The coefficients are negative. Sorry. Negative 9. I think it took it at 0. This is 26. Negative. Yeah. 2, 3, 4. 2, 4. Okay. 2, 4. So that's good. Now you can generalize this for biquadratic equation, quintic equation, or equation of degree 6, or in general any polynomial equation of degree n. Okay. Achha. The last part that I want to discuss is Descartes' rule of signs, or Descartes' rule of signs. Okay. Do you know this rule?
No, sir.
No. Okay. Fine. I'll explain. Now this rule is only an existence rule, meaning it is not going to help us anyhow in finding the roots or finding the values of the roots of the equation or zeros of the polynomial function, but it acts as a good estimator as to where can we find the roots. Okay. First, if the non-zero terms of a single variable polynomial with real coefficients are ordered by descending variable exponent, okay, descending variable exponent, then the number of positive roots is, okay, then the number of positive roots is either equal to the number of sign changes between the consecutive non-zero coefficients, or is less than it by an even number. Let me repeat it again. If the non-zero terms of a single variable polynomial with real coefficients are ordered by descending variable exponent. Descending variable exponent means you have to write the largest power first, and then you have to go for the consecutive descending terms. Now you are supposed to write non-zero terms only. Let's say, for example, in the polynomial you do not have x raised to, let's say you have x raised to 5 and you do not have x raised to 4. Then you are not supposed to write it. Okay, that is not considered as sign change. Okay, then how many positive roots can it have? It is either equal to the number of sign changes between the consecutive non-zero coefficients, or is less than it by an even number. Okay, and even if a root is occurring k times, that is called multiplicity k, algebraic multiplicity k, we count it as n roots, k roots. That means if a root is coming 3 times, we consider them as 3 different roots, or 3 roots basically. Okay. Achha. Now let us apply this part of the Descartes rule to these two polynomials. F of x equal to x raised to 5 minus x raised to 4 plus 3x cubed plus 9x squared minus x plus 5. Okay. Now see here. X raised to 5's sign is positive. X raised to 4's sign is negative. 3x cubed sign is positive. 9x squared sign is positive. X's sign is negative, and constant term is positive. Now how many sign changes are there? Positive to -1, negative to +2, positive to +no, positive to -3, negative to +4. So this has 4 positive roots, or 2 positive roots, or no positive root at all. Okay, I'm not saying 4 is a positive root, the number of roots, okay, number of roots, so no positive. No. Okay, now let's do it here, let's do it for this. Let's do it then. X raised to 5 positive, 4x raised to 4 positive, negative 3x, negative, plus x, positive, minus x, negative. So how many sign changes are taking place? Okay, just a second. How many sign changes are taking place? Positive, no sign change. Positive to negative 1, negative to positive 2, positive to negative 3. Okay, so 3 positive roots or 1 positive root. Okay, fine. Now let's go to the negative roots, but before that we read the 4 point. In particular, if the number of sign changes is 0 or 1, if the number of sign changes is 0 or 1, then the number of positive roots equals the number of sign changes. Well, that's fine. That's a special case of that, right? Okay. Now, let's see whether this rule helps us in finding the number of negative roots. The number of negative roots is the number of sign changes after multiplying the coefficients of odd power terms by -1 or fewer than that by an even number. So basically, we replace x by negative x. Okay, we replace x by negative x. Look here. So it is negative x raised to 5 minus x raised to 4 minus 3x cubed minus, plus 9x squared plus x plus 5. Okay. All the even power terms remain as it is or as they are. All the odd power terms change their sign. Okay, now let's see the sign changes here. Negative, 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 positive, 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 right? So only one sign change. So only one negative root. Okay, only one negative root. What about this? Can we write down the polynomial there? Yes, f of negative x equals negative x raised to 5 plus 4x raised to 4. Nothing is going to happen there. Minus 3x squared minus x minus x. Okay, negative, positive, negative, 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 positive, negative, negative, negative. Okay, 1, 2. So either two negative roots or no negative root. Okay, now here if you see, cubic term is missing, but we did not write it. Okay, the cubic term is missing, but we did not write it. That is how this rule is meant to be applied. That is how this rule is meant to be applied. Okay, now let's verify this on Desmos to understand it better. Have you understood this, or shall I read it again? Okay, so you have to remember that the first part only tells us the number of positive roots of the polynomial, and secondly we get the number of negative roots of the polynomial, and we don't get it exact. If we have more than one sign changes, then we have to say or. Okay, but for 0, no sign change or anything of that sort, we have to say that it's either 0 or 1. Okay. Okay. And even for quadratic equation, this is going to work. Alright, let's go to Desmos now and plot the roots, plot the polynomials here. Okay, plot the polynomials here and verify the. Okay. First, x raised to 5 minus x raised to 4 plus 3x raised to 3 plus 9x raised to 2 minus x plus 5. Okay, is the x raised to 5 minus x raised to 4 plus 3x cubed plus 9x squared minus x plus 5. Okay, so this has only one negative root. Okay, this has only one negative root. Is it consistent with our conclusions from Descartes' rule? Yes. No negative root, no positive root, one negative root. Okay, fine. So we are consistent with that. Next, let's go to the second polynomial here, which has x raised to 5. Okay, which is x raised to 5 plus 4x raised to 4 minus 3x square plus x minus 6. Okay, now 3 positive roots or 1 positive root, it has 1 positive root here. 2 negative roots or no negative root, it has 2 negative roots here. Okay, so 1 positive root, that estimation is correct. 2 negative roots, that estimation is correct. Is that clear?
Yes, sir, but how are we going to determine between the four positive roots?
No, that is something that we cannot determine at least using this rule. Okay, at least using. But okay, so the obvious question is, how can the questions be solved using Descartes' rule of signs? I already told you that this is only an existence rule. like Rolle's theorem or Lagrange's mean value theorem, which are existence theorem or intermediate value theorem, they're existence theorem. So they just say that a root exists or something of that sort is going to exist. What exactly is that root? We cannot determine it. And even the same thing works with this also. We cannot determine how many positive roots or how many negative roots exactly we will have, but we are guaranteed to have something like this. Okay? But see, now the problems in the exam may come like this. If the number of sign changes is 0 or 1, then definitely the number of positive roots is going to equal to the number of sign changes. That is something that should interest you. Clear? Okay. Fine then. So we have completed the theory of complex numbers and quadratic equations.